Chapter 3, Section 3.1. We'll discuss lines in linear growth. What does a constant rate mean? A linear function is a function with a constant growth rate. If you remember, in Section 2.1, we talked about the average growth rate. Here, the average growth rate is constant. A graph of a linear function is a straight line. We can say that a function with a constant growth rate is a straight line. For example, find the growth rate of a function. Make a graph of a function. Is a function linear? For my daughter's wedding reception, I pay $500 rent for the building plus $15 for each guest. This describes the total cost of the reception as a function of a number of guests. Notice here that as you increase the number of guests, the cost for the reception increases by $15 per guest. That is, if you had 30 guests, if you were to add an extra guest, there will be an extra $15. If you had 60 guests, and if you were to add an extra guest, the cost would increase by another $15. The growth rate is the extra cost incurred for each additional guest, that is $15. So the growth rate is constant. It doesn't change as the number of guests changes. The total cost for the reception is a linear function of a number of guests. Here's another example. Find the growth rate of a function and give its practical meaning. Make a graph of a function. Is a function linear? My salary is initially $30,000, and I get a 10% salary raise each year for several years. This describes my salary as a function of time. In this example, the raise depends on the salary. Let's look at the first year increase. Initially, the salary is $30,000, and 10% increase is $3,000. That means for the year 2, the salary is going to be $33,000. Your salary has increased. Now, the 10% of $33,000 is not the same as the 10% of $30,000. After the second year, your increase is 10% of $33,000, which is $3,300. Your second year salary is $36,300. Notice that the increase in salary is different for both of these years. The graph is not a straight line. Therefore, my salary is not a linear function of time in years. These are the graphs of the two examples we just discussed. In this figure, the line represents the cost of the wedding. On the x-axis, you have a number of guests. On the y-axis, on the vertical axis, you have the cost of the wedding. The graph is a linear function. For the second example, the horizontal axis is time in years. The vertical axis is the salary. The graph is not a line. This is an example of a function that's not a linear function. Formula for linear function. The formula for linear function is y equals to growth rate times x plus initial value. Dependent variable is y, this is the output variable, and the input variable or independent variable is x. This can be summarized as y equals to mx plus b. M is the growth rate or slope, and b is the initial value. Every linear function can be described in this form, y equals to mx plus b. Example, let L denote the length in meters of the winning long jump in the early years of modern Olympic Games. Suppose L is a function of a number n of Olympic Games since 1990. An approximate linear formula is L equals to 1400 n plus 7 2/10. Identify the initial values, the growth rate, and explain in practical terms their meaning. Here the initial value is 7 2/10. This is our initial value. That means that for the first Olympics since 1990, this was the length in meters of the winning long jump. The slope is 1400, and this is the constant increase in the length of the winning long jump. The length of a winning long jump increases by this amount from one Olympic game to the next. Example. A rocket starting from an orbit 30,000 kilometers above the surface of Earth blasts off and flies at a constant speed of 1,000 kilometers per hour away from Earth. Explain why the function giving the rocket's distance from Earth in terms of time is linear. Identify the initial value and growth rate. Find a linear formula for the distance. This function is linear because the distance from Earth increases by 1,000 kilometers for every hour. The initial value here is 30,000 kilometers, right? This rocket starts 30,000 kilometers at an orbit around Earth. That's going to be the initial distance from Earth. And every hour, this initial distance is going to increase by 1,000 kilometers. The initial value is 30,000, and the growth rate of the distance is 1,000 kilometers per hour. According to the formula for the linear function, distance is equal to the growth rate times t plus initial value. Here t is time in hours. As we said in the previous slide, the initial value is 30,000 kilometers, and the growth rate is 1,000 kilometers per hour. D is equal to 1,000 t plus 30,000. Interpreting and using the slope. The slope, or the growth rate, can be found by dividing the change in the function by change in independent variable. In this figure, we have m is a slope, and it's equal to change in y divided by change in x. Why do we need this formula? In many cases, we don't know the growth rate, we don't know the slope, but we do know some values of the function. We have some ordered pairs from the function, and we can find the growth rate using 2 points. All you have to do is find the difference in y coordinates and divide that by the difference in x coordinates. What is the meaning of slope? What m means is if x increases by 1 unit, y is going to increase by m units. Suppose your car's 20-gallon tank is full when you begin a road trip. Assume that you're using a gas at a constant rate, so the amount of gas in your tank is a linear function of the time in hours you have been driving. After traveling for 2 hours, your fuel gauge reads 3/4 full. Find the slope of a linear function and explain in practical terms what it means. Here we don't really know the growth rate, we don't know the slope, but we do know that the amount of gas in your tank is a linear function. That means it has a constant rate of change. And we also have 2 points. One point is at time 0, we have 20 gallons. And the other point is at time 2 hours, we have 3/4 of 20 gallons. Given the 2 points, or 2 ordered pairs, we can use the formula on the previous slide to find the slope. In addition to that, we have the initial value, the initial amount of gas in the tank, which is 20 gallons. Right, so the 3/4 of full is 15 gallons, right? 3/4 times 20 is 15. Right, so the change in gas is -5. 15 minus 20 is equal to -5. The change in time is 2 hours. Therefore, M is change in gas divided by change in time, and that's -5 divided by 2, -2.5 gallons per hour. That is our slope. This means we're using 2.5 gallons of gas each hour. In this example, we describe how to convert degrees from Celsius to Fahrenheit. The temperature in degrees Fahrenheit is a linear function of the temperature in degrees Celsius. On the Celsius scale, 0 degrees Celsius is freezing temperature of water, and this occurs at 32 degrees Fahrenheit on Fahrenheit scale. Also, 100 degrees Celsius is the boiling point of water, and this occurs at 212 degrees Fahrenheit. Here we have 2 points. We're given that the conversion formula from Celsius to Fahrenheit is a linear function, and also we have 2 points. These points are 0, 32, and 100 and 212. Right, these are the 2 points. What is the slope of a linear function given the temperature in degrees Fahrenheit in terms of a temperature in degrees Celsius? Choose variable and function names and find linear formula that converts degrees Celsius to degrees Fahrenheit. Make a graph of a linear function. A news report released by Reuters on March 19, 2002 said that the Antarctic Peninsula had warmed by 36 degrees Fahrenheit over the past half-century. The British writer saw a report that the temperatures had increased by 2.2 degrees Celsius. Verify that the temperature of 2.2 degrees Celsius is about 36 degrees Fahrenheit. What increase in Fahrenheit temperature should the writer have reported in part 3? The first step here is to find the slope. The increase on the Celsius scale from 0 to 100 degrees corresponds to an increase of Fahrenheit scale from 32 to 212 degrees. Here the independent variable is Celsius because we're converting from Celsius to Fahrenheit. Our input is going to be degrees in Celsius. Our output, or dependent variable, is going to be degrees in Fahrenheit. Therefore, in the numerator, we have the change in degrees Fahrenheit. And the change in degrees of Celsius is going to be in the denominator. This results in 1.8 degrees Fahrenheit per degree Celsius. This means that if you increase the temperature by 1 degree Celsius, the temperature in Fahrenheit is going to be increased by 1.8 degrees.